Share screen. Start video. Okay. And then we have attendance. Okay. So attendance is up if y'all want to do that while you're waiting. How y'all doing today? Okay. A little tired. Well, we're in the home stretch. Like we're almost, we don't have that much more to go. We can do it. We can do it. Because I'm right there with y'all on amount of sleep and tiredness. I'm with you. I'm really with you. Two more minutes. Some, not, I don't think it was an excessive amount. Better luck next time. I mean, sometimes that's the right decision. You know, you have to weigh your options and you have to say, well, I bet I can do better next semester. And sometimes that first semester is hard. It's not just the classes, it's the social changes and the just like everything. And it's COVID. I mean,
that's the thing with this semester. This is my fourth year. I've never had a semester like this. This was like COVID. It's so different. So if this is someone's first, second semester, like I cannot imagine.
Right.
No, I know.
No, I know. I'm saying it's gonna get easier.
Oh, yeah.
Semester,
Yeah.
Like,
I'm telling you, this is fun. And it's not that these are my hardest classes ever. It's that this semester is so different.
Yeah.
It's gonna get easier for sure.
Yeah, we just need that vaccine. We need that vaccine. I'm going to get my flu shot this Friday. No, I'm going to a pharmacy. I love my pharmacists. They're it's like not Walgreens, not CVS. It's a little local pharmacy, and they're really awesome. They're really awesome. Oh, you do? that is our doctor. That is our doctor. Okay, let's see. I think we are ready to get rolling. So, oh, all right. So attendance is open. If you have not done attendance, please go ahead and do attendance. Okay. All right. So while y'all are doing that, before you came today, you should have watched chapter 8, sections 1 through 3, right? I'm telling you, we are in the home stretch. If you watch the videos before you come to class, you are going to be successful. But if you don't watch them, you're going to be lost. So we're almost there. We have one more exam and the final. So you need to make sure that you come to class ready to go and you know what we're going to talk about. So I want to show you one thing before we talk about the new chapter, the new material. Oh, there's so much stuff. Okay, here we go. So if you come here and you go to the pre-recorded lecture schedule, right? What I had was your exam the Thursday before finals. But Thursday and Friday, y'all aren't supposed to have exams, which I didn't know. I'm new. So we're going to have an exam on just chapters 8 and 9. So that's kind of a good thing for you. You'll have less material on the exam. So I think that'll really help you out. And remember that your lowest exam score is going to be dropped. So once you take this 4th exam, I'm going to look at all your grades and I'm going to pull out the one that's the lowest score. So you'll know what you have before you go into the exam. Okay. So we are over here. We're Thursday right here, section 1, 2, and 3. I don't know why I have that big gap, but that's okay. 1, 2, and 3, which means that Tuesday we're going to finish chapter 8. Now look, this is different. You're going to have a homework due on Wednesday. Usually your homeworks are due on Monday. But just because of taking the exam puts us off, right? You're going to have a homework that is due on Wednesday. So make sure that you do not forget that. Get started on it this weekend. You know, mastering chemistry saves your progress. So you can do a little bit, go do something else, come back. Do a little bit, go do something else, come back, right? It saves your progress. Do not wait to do the chapter 8 homework. I put bonus points in it, just like the other ones. So there's opportunity for bonus there. All right, then we'll do chapter 9 Thursday, and then part 2 of chapter 9 on Tuesday. Then again, you have a homework due on a Wednesday. Then we'll have our exam on Thursday. It's not supposed to be. There we go. Then you'll have your exam on Thursday. And then on Tuesday, it'll be chapter 10, part 1. Thursday, chapter 10, part 2. Your homework will then be due on a Friday, so that I can get all your grades ready to go. You know what you have going into the exam. Okay? So then the next week is exam week. So if we scroll over, then the next week is exam week. And our exam is on the Monday. Questions about that? Let me pull my chat back up. Okay. All good? Yeah? All right. The other thing is, y'all know I updated grades on Moodle, right? What I didn't realize, the way that iClicker works is that you get what are called performance points. So I give you one question. If you get it right, you get a point. If you don't get it right, you don't get the point. That's your performance score. Then every day that we have class, if you click in and answer every one of the questions, even if you got every one wrong, you get 1 point. iClicker separates those points, in my view, like when I log in, but it doesn't separate them for your view. It puts them together. So the score that you see when you go to iClicker.com and get a score is different from what I see on your performance score. So what I'm going to do is I'm going to go in and I'm going to calculate the score that you see on your phone or whatever app you use to log in, and that's the score that I'm going to use. So the ones that are on Moodle right now might be a little bit lower, right, than what you see on your phone. Does that make sense? Because like a couple of people emailed me and I'm like, why? And they screenshotted their thing, you know, and I'm like, that's not what I see. Why is it not what I saw? I finally figured out what it was. So I will update them. I don't know when I'm going to update them. It took me a long time to do it, and I have to recalculate everything. I'm going to do it, but I'm not promising when it'll be done by. But I promise you it will be the score that you see on your device. Make sense? Okay, cool. Questions about that? Good. We all okay on that? All right. Okay. Because I want you to be able to monitor your progress. It doesn't help if you can't see how you're doing. So I want it to be what you see. Okay, let's see. That's all of my stuff for you. All right, so how about we get some more iClicker points? Y'all ready? All right, let's get some more iClicker points. So you did your attendance. Make sure you did your attendance. Okay, here we go. Let's see if I can make this view full screen. There we go. Okay, I'm gonna stop this one, start this one. All right. A single water molecule can make a maximum of blank hydrogen bonds. Minute and a half. What do we have, 46? Oh, I forgot to tell y'all my joke. You want to hear my joke? All right. So what is a witch's favorite test? A spelling test. Not mine though, not mine. But a witch's favorite test is a spelling test. I thought that was funny. I giggled. All right, 10 seconds. Okay, so what did we say? Woohoo, all right. It is 4 indeed. Where are my 4? What are these? That's an acceptor, that's an acceptor. What are these? Donors. Okay, so 4 hydrogen bonds that way. Okay, and this is going to be really important for what we're doing today and kind of the rest of the chapter. So these clicker questions, most of them are what you should know before from what I've taught you. There's only one that's really, there's only one that's really based on the video. Okay, which of the following solutes would you expect to dissolve in water? So which of these would you expect to dissolve in water? Remember your golden rule of solubility. Like dissolves like. Ten seconds. Okay, so what is water? If like dissolves like, water is polar, right? So the other molecules have to be polar in order to dissolve, right? So hexane. In order to be polar, what do we have to have? If you want to be polar, you have to have polar bonds and what? Be an asymmetric molecule, right? So in hexane, do we have polar bonds? Is it carbon-hydrogen bond polar? No, it's not. Good. So can't be hexane. Well, if it can't be hexane, it can't be pentane because all they change are the number of hydrogens and the number of carbons. So neither one of those are right. How about CCl4? Is the carbon-chlorine bond polar? Is one closer to fluorine the floozy than the other? Yes. Chlorine's a next door neighbor to fluorine the floozy. So it's pretty electronegative. So if we were to put bond polarities, we would have to put them on all of the chlorine carbon bonds. But what do you notice about all the vectors of those polarities? What do they do? They all cancel out because this is a symmetric molecule. Right, Caitlin, symmetric. So CCl4 is not polar. How about CH3CH2OH? This is a hydroxyl or an alcohol, right? Polar or nonpolar? Good morning, y'all. Polar or nonpolar? Y'all said it on here. It's polar because it has two lone pairs and it has this hydrogen that's attached to an oxygen, so it can hydrogen bond, right? Can it be polar and not have hydrogen bonds? Absolutely, absolutely. And it would still dissolve in water, yes. It would just have stronger interactions with the water if it were a hydrogen bond. Okay. All right, now, this one we talked about before. A mixture which has evenly dispersed substances is called a blank mixture. Ten seconds. Okay, so what did y'all say? Oh, awesome. Awesome. It is homogeneous. Homogeneous is evenly dispersed. Heterogeneous, you can see like chunks of something, right? How about diluted? What does diluted mean? Less concentrated, right? So it doesn't tell you if it's homogeneous or heterogeneous. It doesn't tell you if it's pure or anything like that. It just tells you the concentration. And then pure, it can't be pure if it's a mixture, right? So it couldn't be those. Good. All right, I think this is the last one. All right, a cup of coffee with sugar is a homogeneous mixture that scientists call a blank. So you've got your cup of coffee, you put your sugar in, mixed it up. It is a homogeneous mixture, but scientists call that a blank. Oh, 5 seconds. Sorry about that. Okay. So what did y'all say? Good. A solution. It's called a solution. So if we have a solution, what's a solution made out of? Two things. A solvent and a solute. Okay. When we're trying to decide if something is a solute or a solvent inside of a solution, why they all had to start with S, don't ask me. But how do we know what the solvent is? Higher concentration. So you have more or a higher concentration. Solute is less and a lower concentration. What is the universal solvent? Water. This is how I remember it, right? If you draw a water molecule, granted it's upside down compared to how we normally draw it, but what shape does it make? A V. So this is a solvent instead of a solute. So water is the universal solvent. So trust me, we are going to say these two words so many times, and if you get them confused, it's going to be a problem. So be very careful that you know solution, solvent, and solute. Okay? All right, so let's skip over. And I'm hoping that we have a few minutes at the end of class to try a few more clicker questions. Because there was one time I was going to try to and we ran out of time. And so I have some from last chapter that we can do. Nope, this one. And this way. Okay. All right. So identify the solute and the solvent in the solutions composed of the following. All right, helix, a breathing gas that is 79% helium and 21% O2 for patients who have difficulty breathing. Which one is the solvent? Whichever one is more is the solvent. So which one is more? Helium. Helium is the solvent. So then what is the solute? Solute is the oxygen. Now this is kind of cool. I'm going to take you on a little side trip because I think this is really pretty interesting. What is the normal percent of oxygen in the air? 20%, just like in this helix mixture. So we know we're 20% oxygen. This is in normal air, O2. It's not very big O. And then what's the other major part of the air we breathe? Anybody know? It's nitrogen, N2. So it's about 80% N2, and you actually have 0.0005% helium. Right? So not very much. That's why we round up the 20 and 80. It adds up to 100, but there's some other stuff in there, but not very much. Okay? So why would we replace nitrogen with helium to help people to breathe? Kind of a weird thing, right? I want to show you something. I really want to show you something. All right, so if we go over here, we go to our periodic table, right? Here's nitrogen. What's the atomic mass of nitrogen? 14.01. What's the atomic mass of helium? 4. Which one is heavier or more dense? Nitrogen. Nitrogen's way more dense than helium. So if we mix helium and oxygen instead of nitrogen and oxygen, it is easier for patients to exhale this mixture because it's not as dense. And so if you have somebody who has a respiratory issue, you can give them this mixture to basically make it easier for them to breathe. So I thought you would probably kind of want to know what that was all about. And you probably never heard of that, right? Yeah, okay. So I kind of figured. Okay. B, children's Tylenol oral suspension containing 160 milligrams of acetaminophen per 5 grams of water. What is the solvent? Water. 5 grams of water is bigger than 160 milligrams. Be careful with that. Solvent. Okay, so what is the solute? The acetaminophen. So be careful not to just look at the number, but look at the unit, right? We know there are 1,000 milligrams in 1 gram. So that would be like saying you have 5,000 milligrams of water. Right? Is that easier to see now? Yeah. Okay. A tincture containing a small amount of an herbal remedy dissolved in alcohol. So what is my solvent? Alcohol. And what is my solute? The herbal remedy. Okay. So now we have to kind of classify different mixtures, right? And I know we said that we have solutions. That's true. We know that a solution is homogeneous, right? And what does homogeneous mean? Consistent composition throughout. So if you had a solution and it had a lid on it, like it's sealed, and you put it down and you walked away and you came back a week later, would you have stuff settled on the bottom? No, it's a solution. So it will never settle. Settle, right? What else is unique about solutions? They are transparent. They are transparent because all of the solute molecules have completely dissolved inside of the water. Okay? There are some substances that will be suspended in water, but they don't completely dissolve. What do we call that kind of a mixture? A colloid. A colloid. So a colloid has substances that do not dissolve. What are some substances that won't dissolve? Remember we talked about fats? They had a polar end and a nonpolar end. So the polar end will associate with water, but the nonpolar end won't. That's an example. Proteins, same sort of deal. Some parts of a protein are polar and some parts are not. So it's another one that won't dissolve. So by definition, these are small particles. So if you have a colloid, it's not going to settle, but it's not fully dissolved. What was my example from lecture of a colloid? Not blood. Milk. Milk. Milk and cream. That's right, milk and cream. My example of solution was coffee plus sugar, right? My example of a colloid was milk. What's unique about milk? If you hold it up to the light, can you see through it? No. So it's not transparent. So because the particles are so small, they stay in suspension. They don't settle. What happens if you have something that settles? What do we call that? A suspension. And no, you don't have to go home because you're suspended. Right? All right, so a suspension. Particles are large and do not dissolve. Because they're large, gravity will work on them and pull them down. So an example of a suspension is muddy water. Has anybody ever, when you were in earth science in high school, did you have a sedimentation tube? Anybody see that? Mr. Foray had one. You didn't take our science. Oh my God. All right, so what you do is like you take a sample from a river or whatever it is, right? And you take all the way down to the bottom, right? And you put it all in a tube and you seal the end of the tube and you mix it up, right? Mix it up really good. And then you set it down and don't touch it. What's going to happen is the bigger particles are going to settle faster because they're heavier, right? And so you'll have the big particles at the bottom, and then gradually the particles get smaller and smaller until you have like sediment. And if you wait long enough, the water will actually clear. And so that's a suspension. I can't believe y'all have never seen that. So cool. Okay, but in the medical field, what's the most common suspension that you're going to encounter? Blood. Right? Because you have red blood cells that are really big that will settle. Okay. All right. So we come down, extend the page. All right. Identify the following as solutions or colloids. A 5% albumin, a protein for replacement fluid. Colloid. Why a colloid? Protein. It didn't dissolve. It's a protein. That's exactly right. Okay. What am I doing? Maybe. Y'all. Okay. All right. B. The electrolyte replacement for fluid lactated Ringer's solution. Okay, that's a whole lot of words, right? If you go buy a Gatorade, what's the advertisement on there? 5 essential electrolytes, you know, and so you'll spend a lot more money on them. What did they put in there? They put salt in there and you just paid for it. Okay, so an electrolyte is something that turns into what? Ions. Right? Electrolyte, I want you to think ions. If it's an ion, by definition, what is it? It's charged. That's a definition of an ion. If it's charged, is it going to interact with water? Water's polar, so it has a partially positive side and a partially negative side. And then we have an ion that's a fully positive or a +1, +2, -1, -2, something like that. Are they going to interact? Yes, they're both polar. So you have an ion dipole interaction, right? Ooh, we're pulling from the last chapter. I'm telling y'all, don't lose it. It will. Yes, it will. So if it's going to interact with water, and it's in a solution of water, right? It's going to dissolve completely. So what kind of a substance is this? It's a solution. L-U-T-I-O-N, solution, yes. Okay, D5W, a 5% dextrose IV fluid. What is dextrose? Has an OSE. Hexose, pentose. Ah, it's a sugar. It's a sugar. How many times have I drawn a sugar in this class? A lot, right? And it doesn't really matter which sugar you draw, but tell me about this molecule. Is this molecule going to interact with water? Water's polar. What does this molecule have lots of? OH. It has our hydroxyl groups. So it is definitely polar. So water is going to surround this molecule. So it is going to dissolve. But I want you to use your common sense. If you have a cup of water and you put sugar into it, what's going to happen? It's going to dissolve, right? And it's going to be a clear liquid. I want you to use the knowledge that you have in addition to what you're learning. So don't separate the two. Keep them together. They're going to help you out, right? Okay, so what is this? This is a solution. Okay. All right. So next. Oh, come on. Oh, there we go. All right. So once we talk about solutions, we're talking about saturated versus unsaturated solutions. Does anybody have a family member who loves to make that old time tea? My grandmother used to do it, right? And so she'd start to boil the water, right? She'd get her tea bags out. She'd pour the hot water on the tea bags. But it was really, really important that she put the sugar in while the water was hot. If you messed that up, she was pissed and you had to start again. So why? What's up with that? Why did the water have to be hot? Do you know how much sugar she put in? It was like cups and cups of sugar. Not a healthy choice, not a healthy choice, trust me. But there was a lot of sugar. So the reason that she wanted to heat the water first is so that all that sugar would dissolve, right? If you've ever made a simple syrup, anybody like to bake? Simple syrup, like to make mixed drinks, also used for simple syrup. You heat the water and then you put sugar in, because simple syrup is such a high concentration of sugar that if you put it in at room temperature, not all the salt would dissolve and it would end up gritty, right? So if something is saturated, it's going to be gritty like that. Why? What is that? Why would it be gritty? Why would it be gritty? Not all the sugar dissolved, right? This is why my grandmother was mad if you waited to put the sugar in, because not all the sugar would dissolve. So that's telling you that you have a saturated solution. If you put so much solute into your solvent that it doesn't all dissolve, that is saturated. And then you have this equilibrium where you have particles that dissolve and particles that crystallize or precipitate out. And it keeps going. So you have the same amount that's in the solid form, but different particles like fluctuate in and out. Okay? All right, so a piece of rock salt that does not change size when added to a salt solution. So I have salt water, and I took a cube of rock salt and I put it in. What happens? Nothing. So is this saturated or not? Yes. So this is, okay. Yes. Saturated. A teaspoon of honey, how is it saturated? Okay, it's a great question. So if you have a piece of salt, right, and you put it in, and that salt does not change size, that means that none of the atoms of salt went into solution, right? So that means that that solution was at its maximum amount of salt that it could hold, right? That volume is at its max. The only way that you could get that salt to dissolve would be to warm it, or you could add more water. If you added more water, then you could add more solute. But at that point, you've got so many solute particles there that you can't add any more because they stay solid. Okay. All right. A teaspoon of honey that dissolves in hot tea. You think you could add a second teaspoon of honey to that hot tea? I bet you could. So is it at its max yet? Nope. not at its max. So we say no. No. So a saturated solution is the maximum amount of solute for that volume of solution. Okay. All right. So let's talk a little bit more about solubility. What we talked about so far was you have a solid and you put that solid into a liquid, right? So like sugar into the tea. My grandmother wanted to increase the temperature of her tea so that she would increase the solubility of the sugar, right? Now, let's see if that applies when we take a gas and put it into a liquid. Now, y'all know how much I like a Diet Coke, right? So that's what I'm going to use for the rest of this. Let's just say I got home, I'm ready to kind of relax, so I want my little treat in the afternoon. I want a Diet Coke, right? So I sit down, I pop the top, it goes, psh, right? Then Charles comes, oh, Mom, let's go outside and play. All right, so what do I want to do? Do I want to leave my Coke sitting on the table, or do I want to put it in the fridge before I go out and play? I want to put it in the fridge, right? Because if I leave it out and I come back an hour later, what is that Diet Coke going to taste like? It's going to be flat, right? What is flat? Okay, let me ask you this. My Diet Coke, why is it fizzy? It's carbonated water. What is carbonated water? Why do we call it carbonated? Must have carbon in it. A gas with carbon in it. What's a gas with carbon in it? Carbon dioxide. That's what makes all your drinks fizzy, is that you have carbon dioxide, a gas, dissolved inside of the liquid. So if I increase the temperature by keeping it warm at room temperature, all my gaseous particles are going to leave my Diet Coke and go out into the atmosphere of my house, right? I'm going to come back to a flat Coke. But if I stick it in the fridge, I'm going to reduce the temperature. If I reduce the temperature, I increase the solubility of my gas. So my gas will stay in my Diet Coke. Now, I know this is like ridiculous that I'm talking about iced tea and Diet Coke. But if you keep these things in mind when you're reading these complex questions, you'll be able to figure it out. So I always want you to think about sweet tea and Dr. B's Diet Coke, okay? All right, so let's see if we can fill in these blanks. We're gonna fill in the blank with increase, decrease, or stay the same. If the temperature of a solution decreases, so my temperature goes down, the solubility of a gas, so the solubility of a gas, will that, go up or down? So when you think about this, I want you to think about, are we thinking about the sweet tea or are we thinking about the Diet Coke? We're thinking about the Diet Coke. A is the Diet Coke. You think I get a sponsorship? Probably not. So if I decrease the temperature, what's going to happen to my solubility? If I put my Diet Coke in the fridge, it's going to be more soluble, or I'm going to have more gas in there or less? I'm going to have more. Okay. Yeah. All right. If the temperature of a solution decreases, the solubility of a solid solute, what is this an example of? Sugar in my tea. Okay. So what's going to happen to the solubility of my sugar inside of my tea? As I decrease the temperature, my solubility will decrease. Okay. Now, if the pressure above a solution decreases, the solubility of a gaseous solute will what? For this, we're thinking about a gas. So is this Diet Coke or sugar and tea? This is Diet Coke. I bet you never wrote that in your notes. So how do you make Diet Coke or regular Coke? You know, that's your thing. I'm not going to judge. How do you get gas inside of a liquid? Pressure. Pressure. It's exactly right. So if you put pressure on a liquid that has gas, the more pressure you put, the more gas is going to go into that liquid, right? So if you increase pressure, you're going to increase solubility. So if the pressure above a solution decreases, so here pressure is going to decrease. This is me sitting down with that Diet Coke and popping the top. If I pop the top, what happens to my pressure? It tanks, right? That's the sound, right? So what's going to happen to the solubility of my gaseous solute? What's going to happen to the carbon dioxide in my Diet Coke? My solubility is going to decrease because it's going out in the air. Pretty cool, right? Now, let me ask you a question. How does temperature affect my Diet Coke when my temperature increases? If I have a Diet Coke and I increase my temperature, but it's closed, my can is closed, what's going to happen to my Diet Coke? The pressure is going to start building up because all of that gas is escaping the liquid. The pressure builds and it will explode. So don't, in the heat of the summer, don't leave cans of carbonated beverages in your car because they will explode in Louisiana. In the peak of Louisiana heat, it has been known to happen. Life skills, causing you to spend a lot of money to clean your trunk. That's exactly right. I have not had to do that, thank goodness. Okay. Same thing with airline bags. What do you mean? Like people put drinks in airline bags? That's crazy. Don't do that. Don't do that. Okay. Explain what is happening in the following situation in terms of solubility. All right, fish die in a lake that is heated with water from a power plant cooling tower. This happens. This absolutely happens. So tell me what happens as my temperature increases. What happens to, let me ask you a different question first. What do fish need to survive? Water? What else? Oxygen. Where's the oxygen? It's in the water. It's dissolved in the water. So, knowing what you know about the Diet Coke and temperature, right? Can you make the same connection between oxygen and water? If the temperature increases, the lake is heated, so the temperature increases, what happens to my oxygen gas inside of my lake? It's going to escape and go out into the atmosphere, right? So as my temperature increases, then I have a decrease in solubility of oxygen gas, that's O2, in the lake water. So O2 leaves water to atmosphere. So this actually happens when plants do things they're not supposed to do. So this is why it's really important to have restrictions and regulations and make them accountable for the impacts they have on the environment. You'll see this happened in my lake last month, really. Oh, that's terrible. Like you like wake up one day and there are all these floating dead fish. It's insane. It is so gross. And then they stink. And then bacteria grow that aren't supposed to grow. And then that depletes oxygen more. It's just like this spiraling out of control environmental disaster. So yeah, there should be regulations on that sort of stuff. Okay, we took a little side trip there. That's kind of fun. All right, so crystals form in a jar of honey that has been sitting for several months. I'm going to tell you that the seal has been broken, right? It's not a perfect seal anymore. So if you leave honey, what's going to happen? What's inside of honey? What's the solute and what's the solvent? Honey is mostly water, but it's got a lot of what? It's very sweet, has a lot of sugar, Yeah, so if it has a lot of sugar and you evaporate just a little bit of water and it crystallizes, what is happening? It's right at that saturation point where you have like almost the maximum amount of sugar that you could possibly have inside of the honey and it still be soluble. And then it sits in your cabinet for a couple of months and it's not a perfect seal. Some water is going to escape. When a little bit of that water escapes, it's going to change the concentration and you'll have a little bit higher concentration sugar and then it starts crystallizing, right? So what's happening in terms of solubility? What should we say? What instigates the crystallization? Loss of, you lose some, not oxygen, but water. You lose some water. Yes, loss of water. So if we lose some water, then what happens? Honey becomes saturated. And the sugar will crystallize or precipitate out or because you've reached that saturation point, right? Honey is really, really thick and viscous because it has so much sugar inside of it. If you ever notice that with simple syrup, when you make simple syrup, like if you compare water, simple syrup, and honey, water's runny, right? Simple syrup is kind of in the middle, and then honey is very, very viscous. And it's all about concentration of sugar. Okay, C, a person receives oxygen through a breathing device. If somebody's struggling to breathe, we put the little, I don't remember what it's called, maybe somebody knows the scientific term for it. You know the little thing they put in your nose, right? So you put them on O2. How does that help them breathe? It's not like being on a ventilator or that compressed air bag, right? Remember the bag we were talking about that you squeeze it and so it pushes air into the lungs? That's not what the little thing inside of the nose does. It's different. It's not increased pressure. Yeah, so you get increased concentration of O2. When we talk about gases and concentration, what property do we think about? Pressure. So the pressure from O2 will increase. They call it the partial pressure because you have many different gases inside the atmosphere, right? But oxygen is only one of them. And so we say that's the partial pressure. So if you have an increased pressure of O2 in the lungs, what's going to happen? More O2 will go where? Just because you get air into your lungs does not mean that you're going to survive. Where does the oxygen have to go? Into your bloodstream. So more O2 will enter your bloodstream. REAM. And then your red blood cells will pick it up and deliver it, right? but it has to get into the bloodstream. So if you have a higher pressure of O2, then you're going to dissolve more O2 into the blood. Just like if you have a higher pressure for making a can of Diet Coke, you're going to have more carbonation inside of that Diet Coke. The higher the pressure you put on that carbon dioxide mixture. So now the higher pressure you do on O2, the more O2 is going to go into your blood. Okay. All right, hyperbaric oxygen chambers contain 100% oxygen instead of the 20% found in the air. These chambers can be used to reverse the effects of carbon monoxide poisoning in the bloodstream faster than what would occur in the air. Based on Henry's law, how is this possible? What's Henry's law? And I don't care that you know that it's Henry's, but what relationship are we talking about? Somebody watched the video, right? Solubility and pressure. Pressure and solubility. So this is very similar to the last question, right? So if you have this hyperbaric oxygen chamber and you're giving all oxygen, right? Every single molecule of gas inside the room is oxygen. What's going to happen? Your red blood cells in your bloodstream contain a protein called hemoglobin. Hemoglobin can bind two things. It can, well, three really. It can bind oxygen, carbon dioxide, and carbon monoxide. Okay? So if it binds carbon monoxide, it can't bind oxygen. So this is why if you inhale carbon monoxide, it basically outcompetes the oxygen, and then you don't deliver any oxygen to your blood cells, and your brain dies, right? And so that's how you die from carbon monoxide poisoning. So why would putting someone in a hyperbaric chamber with 100% oxygen be better than just leaving them in a regular room? You have a higher pressure of O2, right? This is just what we said before. You have a higher pressure of oxygen because you have a higher concentration. Well, if you have a higher pressure of O2, what does that tell you about solubility? You have a higher solubility of O2 in the blood. So if you have more O2 dissolved in the blood, right, then it will replace the carbon monoxide in the blood more quickly. Make sense? So when we talk about gases, we don't really say concentration. We say pressure. But you can kind of think about it that way. All right. Last section for today. Chemical equations for solution formation. So this is going to be really important when we talk in the rest of the chapter, really. We have to understand that when we take different solvents and we mix them with our solutes, what's going to happen? So there are a couple of different things depending on the type of molecule it is, right? If we have something that is ionic, you have something ionic. What's an example of something ionic? A metal plus a nonmetal, or a metal plus a polyatomic ion, or a polyatomic ion plus a polyatomic ion. They're all ions, right? So if they're all ions, what's going to happen when you mix them with water? they're going to dissolve, and not only are they going to dissolve, but they're going to also disassociate. So dissolve means surrounded by water. Disassociate means separate into charged substances. So dissolve is equal to surrounded by water. Disassociate means to separate into, see if I can extend the page, into charged species. So if you have something like KCl, this is a what? Ionic solid, right? We have a metal and a non-metal. So if we add water to it, what's going to happen? Is it going to disassociate, dissolve, or not? Like, tell me about those two things. Is it going to get surrounded by water? Yes. So it will dissolve. Will it also disassociate? Yes. It will turn into an ion of potassium plus an ion of chlorine. So it also disassociated. Things that disassociate, we call them electrolytes, right? So when you drink that Gatorade, in order to be called, in order for them to be able to say, we have 5 different electrolytes in here, you have to have 5 different charged species: a chlorine ion, a potassium ion, I said potassium, did I not? Sodium, potassium, chlorine, any of them, doesn't matter. So you're making a charged species. Not everything that dissolves will disassociate. So the way that we say things is that they are strong electrolytes, weak electrolytes, or non-electrolytes. Strong electrolytes will completely disassociate. Weak electrolytes will only partially disassociate. And then non-electrolytes will dissolve, but will not disassociate. Okay, does that make sense? Sort of? Okay, let's try. I think one other thing I wanted to talk to you about in terms of weak electrolytes. So this is an example here. This is a strong electrolyte that fully disassociates, right? Do you remember when I asked you last chapter, what are the species, what are the functional groups that can form charged things? Do you remember there were 2 of them? An amine can go from uncharged amine to a protonated amine. And then what else? Carboxylic acid. So let's do the carboxylic acid. Right? Okay, we have this, we add it to water. What is going to happen? What was the charged species? Do I remember? Instead of an OH, it ends up being just an O. And because you've lost that hydrogen, you now have a carboxylate, which is a negative charge. And then we have a positive hydrogen ion. So this doesn't happen completely. So if you take this carboxylic acid and you put it into water, some of it is going to stay a carboxylic acid and some of it is going to disassociate. So we only use this full arrow when it fully disassociates or when it doesn't at all. Otherwise, if we're at an equilibrium, we use that equilibrium arrow. So this is important for things that are weak electrolytes who don't fully disassociate. Okay. And while we're on here, let's just draw the very last one. C6H12O6. What happens when you put this? What is this? C6H12O6. It's a sugar. Yes. So if we put this in water, what happens to my sugar? It's still what? C6H12O6. It's still sugar. So the other thing that we have to do is we have to say this is a solid, and now this is in water, so it's called aqueous. So I have dissolved it. So this is dissolved, but does not disassociate. You don't have anything charged, it didn't disassociate. Right. So we can come back up and we can add our states of matter for everything. You start with a solid and you end up with aqueous. If it goes in water, you start with a solid and it ends up aqueous. That's just saying that you put it in water. Does that make sense? It dissolves. It's changing from a solid to an aqueous. It doesn't mean that it's turning into ions. That's electrolytes. Okay, so let's go practice some. Okay, sodium sulfate, Na2SO4, a strong electrolyte, fully, partially, or does not? Fully. So this is the strong electrolyte. Ethyl alcohol, a non-electrolyte. Does not. Good. Hypochlorous acid, HClO, a weak electrolyte. Partially. Okay, now let's go write our equations for these things. Na2SO4 solid. It's a strong electrolyte. Do I need an equilibrium arrow or a solid arrow? I need a solid arrow, and I'm going to put water, because water doesn't really participate in the reaction, but it's there. But water is going to stay water, so you put it under the arrow. Okay, now what's going to happen? I need to make, if I say it's a strong electrolyte, I need to make ions. How do I make ions from Na2SO4? Reverse crisscross them. So now you got to be careful about that. But where are we going to separate this molecule? Between the sodium and the sulfur, or the sulfur and the oxygen? The sodium and the sulfur right there. That's exactly right. So I'm going to make a sodium ion and an SO4 ion. So what should my charge be on sodium? Sodium's a metal. So metals want to lose their electrons, so they're going to be positive. What column is sodium in? You can look on a periodic table, it's okay. I have one like up on my wall next to my desk at home. I do. I also have a coffee mug that I drink from periodically with a periodic table on it. All right, so it's a +1. Now, my SO4, what do you notice? That sulfur and oxygen. Are you going to go to the periodic table for that? No, where are you going? Did you have to memorize that? Oh, please don't memorize that. Please don't memorize that. Where should you go? Your exam resources. What do you have? Polyatomic ion chart. Yay! The back of the book. This is where I got this from, the back of the book, right? So go to your polyatomic ion table. Oh my God, where am I? Okay, SO4, somebody tell me, what is the charge on SO4? -2. -2. Okay. So when I do this, I need to make sure to say that we are now aqueous. We are now aqueous, right? But I have a problem. What's my problem? I'm not balanced. Good catch, y'all. Very good catch. How do I balance this chemical equation? I cannot change subscripts. You may not change subscripts. How do you balance an equation if you don't touch the subscripts? Add coefficients. Okay, so put a 2 in front of our Na, and we are good. Okay, B, ethyl alcohol, CH3, CH2, OH. It's a liquid. It is a non-electrolyte. So what kind of an arrow do I need? I need a solid arrow. I'm going to put my water. Okay, now what's going to happen if it's a weak, I'm sorry, it's not a weak, it's a non-electrolyte. It's going to stay the same, right? CH3, CH2, OH. It doesn't disassociate. It stays exactly the same. But how do I say that it's in water? Because it's in water and it's dissolved. I just say that it's aqueous. Am I balanced? Absolutely. Okay, next in my page. Okay, C. I have HClO, aqueous, and I'm going to add it to water. It is a weak electrolyte. So what's going to happen when I add it to water? It's weak. So it's going to partially separate. Where is it going to separate? If you look on your polyatomic ion table, do you see something that is HCl? No. Do you see something that is ClO? Absolutely. So you're going to split it right there. So you're going to get a hydrogen and you're going to get a ClO. How do I know what my charges are? When hydrogen breaks off, it's always going to be positive. But you could also go and look in your polyatomic ion chart, and what's the charge on ClO? -1. And I know that my charges have to be balanced. So everything on one side of an equation must equal to 0. So if I have a -1 on chlorine on ClO, then you're going to need to have a +1 on the hydrogen. Okay. So now what else do I need to add to this? Okay. Not so bad, right? You already know balancing equations. Do you use, oh, you do. Jason, good call. Oh, ooh, stop, stop. You need to have what? An equilibrium arrow because it's partially. You have some that's staying in the original form that's not charged, and you have some that are disassociating into the ions. So yes, you use the reverse arrows. Thank you. Okay. For the following ionic compounds, write a balanced equation for their hydration in water. FeCl3. It's an ionic compound, it's a solid. So what's going to happen? If it's ionic, it's going to form an ion. So is it going to be a complete, a partial, or a non-electrolyte? Or, you know what I mean? Complete. So it's going to fully disassociate or be a strong electrolyte. Okay, so we have FeCl3, so it's a strong electrolyte. It's going to fully dissociate, so we put a solid arrow. What's it going to make? We only have two different kinds of atoms, so we got to separate it down the middle. You're going to have an iron ion, and you're going to have a chlorine ion. What's my charge on chlorine? Be careful. What's my charge on chlorine? Go look on the periodic table. -1. Now, iron's kind of funky, right? It's a transition metal. How do I find out the charge? If I know chlorine is a -1, if it's a -1, that's where we have a 1 in the formula for FeCl3, right? So where did the 3 come from on the chlorine? Iron's charge. So iron's got to be a +3. So if your chlorine's minus, that means your iron has to be positive. So your iron is +3. And make sure you say that it's in water. So what do we write? Aqueous. Are we done? No. Y'all know, like when I ask, are we done? We're not done. Y'all caught on to that by now, right? I try to like do it, but I just can't keep it up. I can't. So what do we need to do still? We need to balance it. How are we going to balance it? We cannot change subscripts. Put a 3 in front of the chlorine. Y'all are on to my tricks. No, you don't use the Roman numerals because this is a chemical equation. If you were writing it out in words, you would write out iron, I-R-O-N, in parentheses, Roman numeral 3, but only if you're writing it out. So B, NaHCO3. It's a solid, and we're going to put it in water. Where are we going to separate this molecule? Between the sodium and the hydrogen, because HCO3 is a polyatomic ion. So we're going to have a sodium, and we're going to have an HCO3. What are my charges for sodium? +1. What's my charge for HCO3? -1. We're going to say they're aqueous. Are we done? Yes, we are. Oh my gosh, I really didn't leave myself enough room. All right, C, K2SO4. I fit it in the other class. It's going to be a solid, and we're going to put it with water. Where are we going to separate it? Between the K and the SO4. Good. So we're going to have a K, and we're going to have an SO4. We got to say that they're aqueous. What's the charge on K? And potassium. +1. SO4, you get -2. Okay, we cannot mess with subscripts. Are we balanced? We're not balanced. So what do we need to do? Put a 2 on potassium. Aren't these balancing equations nice? Yeah. Yeah. All right, let's see. I'm going to try and squeeze this one in the middle. All right, so I got CaNO3, 2. Put it with water. Where are we going to split it? If it's in parentheses, don't break up anything in parentheses. That's a really good rule of thumb. So we're going to take this sodium, and then we're going to have an NO3. Move my chat over. We're going to have an NO3. So now, what's my charge on my sodium? Not negative. +1. It's not sodium? What? Oh, is it calcium? I covered. Oh, I'm sorry. Hello. Thank y'all. Calcium. Calcium's a plus what? A +2. Thank y'all. And we're going to say it's aqueous. And NO3, we're going to say is aqueous. What's our charge? -1. All right. Am I done? No, I'm not done. What do I need to do? I need to put a 2 in front of the NO3. All right. Okay. So when we're in the medical field, right, sometimes what's important is not the ion that we're giving our patients. It's how much of a charge we are giving our patients. The body cells don't always distinguish what ion it is, but it does look at the total charge inside and outside of a cell. And so a lot of times it's very, very important that we monitor how much charged stuff we give our patients. So in order to really think about that, we can't just say, I'm giving 2 moles of calcium. I'm giving 2 moles of potassium. What does that really mean to the body? Well, what's the charge on potassium? +1. What's the charge on calcium? Is that the one I use? +2, right? So if I give someone 2 moles of potassium, how many moles of charge am I giving them? 2 moles. But if I give them 2 moles of calcium, which is a +2 charge, how many moles of charge am I giving them? 4, right? Because 1 atom of potassium has a charge of +1. So for every 1 mole, I give my patient 1 mole of charge. But calcium, for every atom, it has a +2. So for every mole of calcium that I give to my patients, I'm giving them 2 moles of a plus charge, okay? So what do we call that amount of a charge? We call it the equivalence, okay? And we abbreviate it EQ. So how many equivalents of Mg2 plus are present in a solution that contains 2.5 moles of Mg2 plus? So if we start out with 2.50 moles Mg2 plus, oh y'all, it's back to dimensional analysis. Told y'all it wasn't going away. So if I have 2.50 moles of Mg2 plus, what equivalence is that? If I have 1 mole of Mg2 plus, what's my equivalence? It depends on your charge. So what's my equivalence? 2. Y'all all right? So 2, and we just call it EQ, and then you say what substance it is. Okay? So my moles will cancel. So 2.5 times 2 is 5. So I'm giving them 5 equivalents of Mg2 plus. What if I had 2.5 moles of K plus? How much am I giving my patient? I'm giving them 2.5 because 1 EQ of 1 plus, not a 2 plus, but 1 plus. Extend the page, right? 1 mole of K plus, right? So I'm giving them a different amount of charge, EQ. Make sense? All right, so I think we're almost done. 8.2, we only have 1 left. All right, I'm gonna do it real quick. So it's the same thing. We have an IV, we have 5% dextrose and 35 milliequivalents of potassium per liter, right? If we have a milli equivalent, what's a milli equivalent? What is that? It's like a milliliter, right? So if you have 1,000 milli equivalents, that's going to give you 1 equivalent. Just like you need 1,000 milliliters to equal to 1 liter, same thing. So if you've got 35 milli equivalents of K plus per liter of solution, right? If our patient receives 235 milliliters of IV, how many moles of potassium were delivered? So I just need to convert. I need to cancel out my milli equivalents. And I know I have one equivalent and 1 milli equivalent. So that cancels. But I need to go from equivalents to moles. So I know in 1 mole of K plus, I have how much equivalents? 1, because it's a charge of 1. But I'm giving them 235 milliliters. And here it's liters. So I need to convert that. 1 liter, 1,000 milliliters. So my liters cancel. Now I'm in equivalents per milliliter. So you can just multiply by 235 milliliters. And you should get your answer, which should be 0.0082 moles of K plus. Okay? All right, the end. See y'all next time. Don't forget to watch your videos. And I was having a little bit of a problem with YouTube. So I have the first 2 up. The other 2, I don't know, something's wonky, but I'm going to fix it this afternoon. Okay? So they'll all be up shortly. Any questions on Zoom? Y'all good? All right.
Do you think, okay, I'm not into grade. I just like I couldn't study this last week. But should I take time to like try and relearn last chapters before this test?